Hello, students. We're going to focus on electrochemistry. And so I would focus in chapter 18 in your chemistry Zumdal book on sections 18.1 through 18.4 this week. So we're going to cover highlights. To do that, we're going to review a little bit of information from previous from Chem 200 material. So oxidation is the loss of electrons, while reduction is the gaining of electrons. And so that is something you should have learned already in previous courses. Just as a reminder, again, that we have these terms oxidizing agent. Oxidizing agent causes oxidation, and so it itself is reduced. So it's opposite of what you'd think. The reducing agent causes reduction, so the reducing agent is oxidized. Okay, so make sure you know those definitions. This is super important. So I know that we're have very little time left in the semester, but so I'm going to highlight really important things to take from this section, and this is one of them because you're going to see that terminology later in other courses. So let's say last semester you did this, you dropped zinc into hydrochloric acid to make zinc 2 ion and hydrogen gas. So we know that this is an oxidation reduction because the zinc went from a zero charge as an element, elements are neutral, to zinc 2 plus, and so it lost electrons. So because it lost electrons, it is being oxidized. And it is going to cause the hydrogen ion to go from +1 to 0 and be reduced. And so the zinc is the reducing agent because it's causing the hydrogen ion to be reduced. The hydrogen ion gains electrons. It's going from a +1 to 0. So it's being reduced. It's causing zinc to be oxidized. So it is the oxidizing agent. So this is also a very important slide, okay, that you understand whether something is being oxidized or reduced. Now, in this example, this is a pretty easy reaction. They're not always that easy. So if I have a reaction of dichromate plus iodide to make chromium 3 and iodine, this is also a redox. And so the first question that I'd like to pose is, how do we know it's redox? Will we be able to identify oxidation and reduction and oxidizing and reducing agent? So to do that, what we do is we split them into what are called half reactions. Okay, so they're going to be split into half reactions. Now, one of the things that's interesting about these redox is that a lot of times they'll show the reaction as a net ionic. So if you notice, we don't know if it's sodium dichromate, potassium, sodium iodide. It's not giving us that particular information. So a lot of times they just show as net ionics. The other thing too about these kinds of reactions is that they tend to prefer acidic environments or basic environments. Okay, and we don't know that unless we're told which way it's going to go. So like this one is actually acidic, but we'll talk more about that in just a second. So to understand what's going on with them, what we would do is we would assign oxidation numbers. Maybe this is review. I'm not sure, but sometimes the oxidation numbers are easy to spot. So this has a negative charge. So for sure its oxidation number is -1. And then our elements are always 0. So if you notice there, iodine went from -1 to 0. So it lost an electron. So that must be an oxidation. And since it's oxidized, it must be the reducing agent. Okay, now in the case of the chromium-3, the charge on that guy for sure is +3. And then now we want to know what's the oxidation of the chromium in dichromate. And this is where we need to have some help. So to determine its oxidation state, there's certain ones we're always going to know. Oxygen is 2- unless it's in a peroxide, and then it's a 1-. And then O2 would be 0. Okay, but here it's within a ion, so it's going to be -2. Hydrogen will be +1, unless it's like H2, the element, which would be 0. Fluorine's always -1. And these are the ones that we know, and then we'll use them to find other metals or elements within the formula. So like for this guy, we know oxygen, there's 7 of them at 2-. And we don't know the charge on chromium, so we have 2 of them. And it has to equal the overall charge of -2. So the question would be, what's our x? And if we solved for x, we would see that it's +3, right? Because 6 minus 14 is -2. Oh, I wrote, sorry, I don't know why I wrote +3. +6, yeah. So 2 times 6 is 12, right? Plus -14 equals -2. I think I made a mistake on what I just said a second ago. So our oxidation state on the chromium is +6. So it went from a +6 to a 3+. So that must have gained electrons. And so that was a reduction. So that is an oxidizing agent. Okay, so I will ask questions. So I'm going to put know how to find the oxidation state Okay, and in your homework that I've assigned, there'll be some practice for that. Okay. Now, balancing redox. Okay, normally this is a big thing for us, but I feel like I have to make some decisions on what to keep and what not to keep as far as testing, because we're kind of down to the wire. So this one's going to be what I call an FYI. It is important, and normally I cover it. So I'm just going to go through it with you guys, but I won't test on it. So I guess you might be fast forwarding me right now, but let me just show you how we go about this. I feel like I obligated to show you. Now, in the case of redox reactions, we would be given information on whether it likes acidic or not, and it does in this case. And then the balancing is kind of complicated. So we have 2 chromiums here, so I put a 2 here. We have 7 oxygens, so there'd be 7 H2Os added to the side. Now, if you're asking why water? Because these guys are all aqueous. And so we'll use water's involved, and it's implied in the reaction. Okay, now that I have 7 oxygens, I have 14 H+. Why did I use H+? Because it's in acidic. And then now I need to balance electrons. the charge, right? So I have 6 plus on this side. I have 14 plus and a 2 minus, so I have 12 plus on this side. And I asked the question, how many electrons should I add to make them the same charge? Now, they don't have to be neutral. So I just need to get the 12 plus down to 6 plus. So that would be adding 6 electrons to this side. And so now I have my half reaction. The other one's extremely easy compared to this one because I just am going to balance the 2 iodines. I don't have oxygen or water H plus to deal with. I just need to balance the electrons. So I have 2 negatives here, so I put a 2 electrons over here. Okay, and then now I'm going to combine the 2 equations. This one here is gaining 6 electrons. This one's losing 2. So they need to be the same. So I'm going to multiply that one through by 3. And then I'm going to combine them. So I'm going to say 6 electrons plus 14H plus dichromate plus 6 iodides makes 2 chromium 3s, 7 waters, plus 3 iodine, and 6 electrons. And notice we did a good job because the 6 electrons would cancel out. Okay, so there's a lot going on with those. And normally I would encourage you to practice them as much as possible. But under the circumstances, I want you to have this as an FYI that there's a special process for balancing redox reactions. Okay, electrochemical cells, super important. Really the heart of the chapter. There's going to be 2 kinds of cells. There's voltaic cells and there's electrolytic cells. The voltaic cells are cells that are spontaneous reactions. Delta G is less than 0. And so these are the types of batteries that we work with in real life. They provide energy. So like the lithium ion batteries, the Duracell batteries, those guys are all voltaic cells, spontaneous chemical changes that release free energy to do work. Electrolytic cells are the opposite. They require electrical energy to drive a non-spontaneous reaction. Okay, so voltaic cells, you're responsible for really knowing them well, both in concepts and in calculation. Electrolytic will only be conceptual. Okay, both cells will be used or constructed in a way that would have been fun to do in lab, but we are just not having that right now. So you have to rely on the pictures, but I'll show you a picture in a minute. Some really important terminology. The anode is where oxidation occurs. The cathode is where reduction occurs. Okay. So for sure, know those, understand the difference in terminology. Okay, let me show you a battery. Basically what a battery looks like, a voltaic cell, also known as galvanic, is that you would take a piece of metal, put it into a solution, an electrolytic solution, an ion solution, and then you would force the electrons that come off of that oxidation to go through a wire, and then you'd attach it to another metal on this side, and then the electrons would go through that metal, and then it would actually reduce what's in the solution. So from here, if you picture the electrons start off in this metal, go through the wire, go all the way through the other side, through that metal, and reduce. So our anode is oxidation. That's where the oxidation is going to happen. And then on the other side where the reduction occurs is called a cathode. Okay, when a voltaic cell releases energy, it's spontaneous. And so that's the whole point of a voltaic cell, is to release electrons to do work. An electrolytic cell is different. It requires energy. So, I really like the lithium ion battery example on your cell phone. All day, that's a voltaic cell. It's releasing a lot of free energy to power your phone. And then at night, when the battery's dead, remember from our previous discussions, delta G at that point 0, no more work, then we have to provide an outside source of energy. So you have a power supply, you have an outside current, and that's going to force a non-spontaneous reaction to happen. The anode is still oxidation and the cathode still reduction, but you're going to force the electrons into this system. Okay. We'll come back to this conceptually. So this guy's just in concept you need to know. So we'll finish it up at the end. But voltaic cell is really, really important in terms of calculation and concept. Okay, one last thing as we move forward. The anode is where the source of electrons is. So do you notice here the metal is given a negative symbol? That's because it's the source of the electrons. The positive side is where the electrons flow towards. So you've seen this designation in a battery, right? It has a plus and a minus end. So the negative end's the anode where oxidation is. The plus side is the cathode where reduction is. Okay, so let me show you this really great graphic here. What this is showing you guys is that we can make a spontaneous reaction between zinc and copper 2. Now here's the interesting part. The zinc's over on this side in this flask, and it is going to start to react, and electrons are going to start coming out of it. We're going to force it through a wire to the other strip of metal on the other side, but that's going to be going through there and reacting with the copper 2 that's in that solution. So we're separating our reactants away from each other, but it's the metal here, so here's the metal, reacting with the copper 2 in that solution. The only reason why you have this piece of metal on this side is to conduct the electrons through to the solution. And so then you form zinc 2 plus and copper. Okay, so this nice reaction down here. Okay, so here's a nicer picture of it. You have the zinc. It's the metal. It's going to start to lose electrons. We'll talk more about how we know that. It's going to lose electrons through the wire, come to the side. Now the electrons are going to flow through that copper metal. They're not reacting with each other. The electrons are going to go into the solution and react with the copper 2. So the oxidation side is the zinc going to zinc 2 plus, losing 2 electrons. The copper 2 in the solution is going to gain those 2 electrons, and then you can balance those 2 equations for the overall cell. So this whole thing's called an electrochemical cell. Now let's talk about what happens. The zinc's reacting, right? The zinc's going to decrease in mass because it's going to get used up. The electrons will flow through the metal that's there. You see how that's showing the electrons flowing through the metal and then go through the wire. On the other side, the copper is going to increase in mass because those electrons are going to flow through and react with it to form more copper. So we see an increase in the copper side. So the anode decreases in mass. The other thing that happens, you see how zinc 2 is formed? It's going to increase in amount of positives, and that's going to prevent over time the desire of the electron to go through the wire if this starts to increase in positive charge. So we have a salt bridge. What the salt bridge is, it's a salt. And to keep that zinc 2 from being too highly charged, the sulfate from that salt is going to come, or the negative one, it didn't have to be sulfate, usually a soluble salt, is going to come into here. And what's that going to do is keep this neutral so that the electrons still want to flow through the wire. On the other hand, on this side, it's going to get less positive, right? Because copper 2 is reacting. It's going to get less positive. So to prevent that, the sodium ion from the salt is going to come in here to keep it more positive so that the electrons still want to flow. So electrons in a voltaic cell always flow from anode to cathode. And this is just you can read it more carefully. It's what I verbally just said, but it's written out for you. Over time, the zinc gets corroded, right? Reacted. It's going to weigh less. It's going to, right, it reacted. And then over time, the copper side's going to gain mass because you made copper. Okay, so the anode produced electrons, and so the anode is always negative in a voltaic cell. The electrons flow to the positive side. The positive electrode in a voltaic cell is always the cathode. There's the role of the salt bridge. So I already said that. You can read this more carefully. Okay. Let me talk about active and inactive electrodes. And let me go to the next example, then we can come back to that slide. Okay, in this case, this is the reaction of a little bit more complicated one, the one that it was similar to the one that I balanced earlier, similar. So here you have iodide ion. It's losing 2 electrons. Iodide ion is water soluble. The product is iodine solid, I2, neither of which you can clamp a wire onto. So because you can't clamp a wire onto those guys, you have to use what's called an inactive electrode or inert electrode. The choices for inert means unreactive. So you don't want to put something in there that's going to react. So inert electrodes, one could be carbon graphite, as shown here, and that's what we would have used in our lab, or platinum. We used to use the platinum, but it's expensive, right? So we'd always have it kind of under lock and key. It got too stressful. So in this case, a carbon graphite was used. Okay, and the reason it's a practical reason, you can't clamp a wire onto things that are aqueous or powdery solids like iodine. So here's the carbon graphite. Okay, so the I minus is in solution with I2, and it's going to lose electrons. It's the anode, it's going to flow. Notice it's negative. Anodes are always negative in a voltaic cell. Going to flow to the other side. Now, on the other side is permanganate, acid, and Mn2. And on that side, the permanganate ion is reduced. And again, none of these three, you can't clamp a wire onto them. So from a practical point of view, that's when we use an inert electrode. It's okay on this side because the electrons are just flowing through that metal to get into the solution and cause reduction. Okay, so inert electrodes are used when whatever species are involved are not able to have a wire attached to them. Okay, the cell notations are important because if I want to tell somebody, hey, I want to make a voltaic cell, then I don't want to verbally say it. I don't want to say, take a piece of zinc, put it in zinc nitrate, use the salt bridge, put on the other side in a beaker copper with a piece of copper. It's too wordy. So what we do is we just do a shorthand notation. This is pretty easy. On this side, we show our anode. The double lines is the salt bridge. So we're telling somebody to don't forget to use a salt bridge or else the battery doesn't work. Cathode. And then you tell somebody what is in that solution. So I used a piece of zinc, right? In that previous picture, it had the zinc. It had the zinc ion. That's our anode. The electrons flowed to the other side to a solution of copper 2 with a piece of copper. Now, the only thing to consider is that states of matter matter. So the zinc, you need to tell somebody it's a piece of solid. And then there's this line, the single line just shows a phase boundary. So in other words, the zinc's a solid and the zinc 2 plus is in solution. The copper 2 is an aqueous, and then you have a copper solid. So that's why the line is used there. Okay, now this guy was from the other picture. If you want to go back and take a look, you should. Here we had the one with the graphite. And this one looks a lot more complicated, but it looked like this. It had the copper graphite. In the solution was I minus and I2 solid. Remember this? We just looked at it. If you need to, go back and look at the pretty picture. Then you had the carbon on this side, and in that solution was a more complex redox, like the one that I showed you for balancing, that needed an acid. Okay, now if we look closely, we're going to tell somebody, okay, I need to use graphite. You could put C if you want as well. Sometimes I write it like this. Okay. Different line, right? Different state from, okay, now let's look at what's in solution. I minus. Now that's an aqueous and this is a solid. So I'll put a line, I2 solid, and then salt bridge, not shown. There, I put my salt bridge in. And then on this side, permanganate, excuse me. It has H plus, it has Mn2 plus, and then carbon graphite on this side. Okay, now why are all these guys commas? Is because they're all aqueous, so they're all in the same phase, so just use a comma. The I minus is aqueous, but iodine is a solid. That's why there's a line. Okay, and then so this is a shorthand notation so that if you see the shorthand, you know how to build the battery. And then again, always anode first, double line, cathode stuff. Okay, so what I'd like you to do is to read this one and then answer the question. So draw a diagram, show the balanced equations, write the notation for the Voltaic cell. It's with chromium solid and chromium 3 nitrate. And on the other side, you have what does it mean by bar? It means a strip of chromium. And the other half cell is a strip of silver in a silver nitrate solution. The salt bridge is potassium nitrate. Okay, so pause this and write this, and then double check your answer. And here's the answer. And so for sure, expect this type of question on your test. This is like the most important part of the chapter in some ways. Okay, it's understanding how these batteries are built. It is a shame that you couldn't build one. It is, I'm going to try to see, because there are some like fun demo ones that sometimes they have kids build. So I'm going to try to find one of those, and maybe you have stuff in your house that you could build one, just to give you a feel for it. Okay, so you can pause me now and double check your answer. One important thing is that the electrons have to be balanced. So this one was 1 electron. This one gave off 3 electrons. So you do have to multiply this through by 3 to get an overall balanced equation. Okay. Okay, the next part of this chapter is really important as well. And it's because we're going to answer the question, why did the zinc lose electrons to the copper tube? So in other words, why did it flow that way? So this has to do with what are called electrical potentials. And so let's take a look at the numbers. I like looking at it from a math point of view. Oops. I'm going to get to my charts. Oh, I didn't get there yet. Okay, so hold up. Let's go back then. Sorry. Okay, so why did zinc lose electrons? Is because it has a much stronger ability to lose electrons. So it is a much stronger reducing agent. It wants to lose electrons. And we're going to talk about that in mathematical terms. Sorry, I thought it was next, the math part. The copper, on the other hand, it has a much stronger affinity to gain electrons. Okay, so a spontaneous reaction will occur only when the species that has a strong affinity to gain is being reduced, and the one that has a strong affinity for oxidation is oxidized. In other words, if we tried to do this, zinc 2 plus copper, this direction, that's a no-go. The elements are not in their natural potentials in that form. It has to be zinc losing electrons to copper. Okay, and we're going to see how we're going to know this with some very, I think, user-friendly tables coming up. Okay, now the desire, I guess you'd say, for zinc to lose electrons. Oops, yeah. And the desire for copper to gain them, to form that voltaic cell we just drew. If you need to, go back to the pretty picture of it. Okay, so the desire for zinc to lose and the copper to gain creates a what's called an electromotive force. That's the drive of zinc to lose electrons to copper. And that drive sets up what's called a cell potential, and that's measured in voltage. If you're going to have a spontaneous process, the voltage of the cell has to be positive. So E of cell has to be positive, the voltage, for a spontaneous battery. So all voltaic cells, if set up correctly, are spontaneous and have a positive voltage. Okay, and again, we're going to use some charts here in a minute. Just so you know, when you see E naught of cell, that's going to be standard conditions, back of the book stuff. All the solutions would be 1 molar. All the gases involved, if involved, are going to be 1 atmosphere. Here's some common voltages from regular things in life. So a common alkaline flashlight battery is 1.5 volts. A lead car battery is 2.1 volts. If you're wondering, that seems small, but in a lead acid car battery, it's actually 6 cells. A calculator battery, 1.3, lithium ion, 3.7. See what a very high energy battery. Okay, and then here's some electric eel, 0.15, and the nerve of a giant squid, 0.070. And at the end, I'm going to speak a little bit about applications of this in biology and biochemistry. Okay, so measuring a standard cell potential, so this is that electromotive force, the voltage of a battery, requires a voltmeter. So in the case of that zinc copper battery that we've been talking about here, the voltage of that is 1.10 volts. And you might have used in real life voltmeters, so that's measured by a voltmeter. Okay, so how will we determine that voltage? How will we determine that cell potential and the energy we can get from it? To do that, we are going to look at what are called standard cell reduction potentials. Okay, and they're all going to be written as reductions. And these ones are given to you. So this is a given on your test. These reduction potentials that we're going to look at in a moment, they had to be measured experimentally. And so they are measured relative to a standard reference cell. And that standard reference cell will be hydrogen's electrode. It's called the standard hydrogen electrode, or the SHE. In that standard hydrogen electrode, it consists of a platinum electrode. Why platinum? Inert, because hydrogen gas is a gas, H plus is an acid, and so you cannot connect wires to those guys, so it needs an inert electrode. The hydrogen ion in that cell is 1 molar, so standard, and the H2 gas is 1 atmosphere. Now, in our lab, we wouldn't be able to use the SHE because hydrogen's flammable, and so this would be very dangerous for us. So we would not have been able to show this to you. So here's a nice, beautiful graphic regarding the SHE, the standard hydrogen electrode. Okay, let's look over on this side. Here's the platinum wire. It has H plus, right, acid. It has within it, it didn't show, but put into this is gas is pumped into it at 1 atmosphere. Okay, and on that side is the reduction. That's the reduction half reaction. So I know it's showing H3O plus. I prefer more simple to H plus. On the other side of the electrochemical cell is the zinc metal in the zinc ion solution. And so that's where the anode is. And then there's a salt bridge. Okay, so if I was going to write this one out in the standard, or sorry, the abbreviated notation, it'd be zinc line, zinc 2, right? On salt bridge. On the other side, H plus, separated from hydrogen gas, separated from the platinum. Those guys here, that's aqueous and gas, so it needs the line. Okay, now some references use a comma here. We'll just keep it simple, put the line since it's in a different state. Okay, so this one, when it's hooked up, the zinc, when it's hooked up to hydrogen on the other side, the electrons spontaneously flow from zinc through the wire coming this way. The voltage for that cell is 0.76 volts. Now, here's what's interesting. That is going to be the value for zinc losing electrons to, I'm sorry, I didn't mean to put a plus there. So that is the cell here where zinc's losing electrons and the H plus is gaining. Okay, now here's the important part to this. The hydrogen value, okay, the hydrogen ion was gaining, correct? It's assigned a voltage of 0 as that reduction because it is the standard. So that was arbitrarily set at 0. The zinc was oxidized. Okay, and the overall cell, and that was 0.76 volts. So its oxidation potential was given a value of 0.76 volts. This would be the reduction potential, and added up together gives us our overall cell value. And that value is plus 0.76 because the electrons spontaneously flowed from zinc to H plus. Okay, now what we're going to see in a moment is that we're going to put these values into a very famous chart in chemistry called the reduction potential chart, standard reduction potential. Everybody on there is going to be listed as a reduction. So zinc here, as I've written it, the way it was measured on that cell we just built and looked at, is the oxidized one. Its oxidation potential is plus 0.76, but when it's written on the chart, that's reduction. It's going to be listed like this as a reduction. And if you have any idea on how that would look as a reduction, that's going to be switched in sign. So if it's as an oxidation, it's 0.76 volts. As a reduction, it's negative 0.76 volts. So always keep this in mind that if we flip them, the value of the potential stays the same, the sign changes. Okay, so let's see if that's true. This is our selected standard electrode potentials. They're all listed as reductions. I don't know why it's not working. Okay, I don't know why it stopped working on me. So it has reduction potentials. And if you look, see where it says 2H plus 2 electrons to hydrogen, that's our zero. Okay, and when we look at that, that is our standard. Compared to hydrogen, zinc wanted to be oxidized, right? That's where it got spontaneous. Now on this chart, it's going to be listed as a reduction. Notice here's the negative 0.76. But what I want you to realize is that the way this chart works, let me get back my pen. I don't know why it stopped working. Wow, that's weird. Okay, well, maybe the highlighter. We'll try that. So here's our hydrogen. Okay, any values below that, so all of these here below, these guys want to oxidize compared to hydrogen. Their potentials will be more negative. Now, any of the species above, those want to reduce compared to hydrogen. So this is actually the most important chart for us. We will always read them as follows. The ones at the top with the more positive potential, that is a species that wants to be reduced. The ones on the bottom want to be oxidized, and therefore, in writing the equation with them, they're going to get flipped, and their signs are also going to change. So we're going to practice this in just a moment. So compared to hydrogen, lithium is oxidized. Compared to hydrogen, silver ion is reduced. So anything above hydrogen is reduced compared to hydrogen. Anything below hydrogen is oxidized. Now, it doesn't have to always be compared to hydrogen. So overall then, values, species up on the top of this chart, the more positive they are, the more they're going to be reduced. The more negative they are, the more they're going to be oxidized. And the more negative one has to be flipped. The other important thing on this chart, very, very important, is that then up at the top, the strongest species for reduction is F2. Since it wants to be reduced, it's the best oxidizing agent. At the bottom of the chart, lithium solid wants to be oxidized the most. It's the strongest reducing agent. Okay, so that for sure is going to be on your test. Is given this chart, you're going to have to be able to predict who's oxidized and who's reduced. Okay, so let's go to